Welcome Calculus 3 students. We are in chapter 13 now. We're extending everything in 3 space. Our plane in 3 space is going to be defined by this vector. And it must be a non-zero vector and a fixed point in that plane. After which there will be a normal vector, here it is right here, a normal vector that will be orthogonal to all other vectors in that plane. Okay, so we need to get an equation of a plane, and we've been given the definition and the general equation for that and how it will be presented. So let's go ahead and try to get one of these. First it says that we need a point. Well, we've got one. And we need a normal vector. We've got one of those too. And it's going to be described by the equation. Now A, B, and C are those numbers that are represented by the component vectors of your normal. So that would be -1 times x minus my x naught. Now that's the x in that P point, so that would be minus 2, and then plus the B, which would be 2 times, and then y minus the -3, and I'm going to plug all those in. Alright, I was just doing my computation here. 2 and 6 are 8, minus 12 is a -4, moving it to the other side, there's my 4. And my general equation is right here, where we say that these values here, the A, B, and C, are the orientation of the plane, and the D point right there is what we are going to call the location of the plane. For example 2, we're given 3 points, and these 3 points are going to determine this plane. We would know that PQ and PR are vectors that lie in that plane. We'll need to get a normal vector to these, so we'll need to do the cross product back from the Dark Ages in last chapter. So the first thing I'm going to do is get PQ, vector PQ, and vector PR, so that I can then take their cross product. So I'll write those down, do that subtraction, and write it down. Alright, I did that subtraction, and then I wrote down how it is that I'll get the normal vector, and then after doing that determinant, I'll get 10 as my I component, and 8 as my J component, and 10 as my K component. Next I'll be just playing the same game I did last time, using this equation here and using this point P as my P naught, and so I'll write that down. Doing my computation, this is what I get for the equation of the plane. I could rewrite it as this because it's actually double what it could be. They are the same. And this is the simplified version. Alright. We're just looking at example 3, and they've given us the equation of the plane. We don't have to find it this time, but we could pick out the normal vector. The normal vector here is just those coefficients, 2, -3, -1, with D being my location. They want me to find the points at which that it intersects all the different axes. So if it intersects the x-axis, that means that y and z must be 0. So 2x equals 6, at x equals 3. I have an intersection point, so that would be the point 3, 0, 0. Likewise, I'm going to do that for the y-axis. I'll let x and z be 0 and carry on. So that's what I get for the B part here, the different points. C says describe the set of points where it intersects the YZ plane. That means x is 0 there. So for the YZ plane, if x is 0, we have negative 3y minus z equals 6. So any of the points that satisfy that particular equation, and I'm going to do the same for the others. Alright guys, pretty straightforward so far, isn't it? Just making the parallel between three-dimensional space and two-dimensional space, and you're not really doing anything different. It's just now we're in 3 dimensions. By our definition of parallel and orthogonal, two planes are parallel if their normal vectors are parallel. That means I'm going to find their normals, and if they're just scalar multiples of each other, then they're going to be parallel. Now they're orthogonal if their normal vectors are orthogonal, means I'll have to do the dot product, and if their dot product is 0, then I know that they're orthogonal. So I'm going to go ahead and get the normal vector for each of these equations. Looking at these, I can see that Q and R, because you could say that I'm multiplying everything here by a -2, and I would get Q. So I know that Q is parallel to R. And I can look at S and T and see that I could multiply by, looks like 2/3. Let me check. No, it's 3/2. It's -3/2. Yeah, and if you do, then you'll see you get the other one. Just doing the dot product here just to see. I know that Q and R are not going to be orthogonal because they're parallel. I need to see if I did Q and S, and I found that they're orthogonal, so that means R is going to be orthogonal as well. And I'm going to do T now to see, well, yeah, it would be because S and T are parallel, so I guess once I do that, then I know that Q and S are orthogonal, R and S are orthogonal, and then Q and T and R and T are orthogonal. Okay, so I don't have to do any more. Okay, I'm going to find an equation of a plane, and it's going to pass through this point, and it's parallel to this guy. So that means, since it's parallel, it's going to have the same normal, so it's just going to follow that same general equation, but without this D for the location. So I'm just going to plop that down. Alright, just plopping that down, just doing the computation. There's what you get. The next one is a little bit trickier. Let me give myself some space. Okay, I've written down the normal vector for each. Just notice that we're supposed to find the equation of the line of intersection of those two planes. First off, let's make sure that they're not parallel, because that would make it really easy. But they're not. Their normal vectors are not scalar multiples of each other. So that means that these two planes, and imagine two pieces of paper, these two planes are going to intersect in a line, and I'm supposed to find the equation for that line. First off, I'm going to have to find some sort of place where they intersect. So I'm going to figure out first where they intersect in the XY plane. So I'll do that first, and how I figure out is just like I did before. To figure out where they intersect in the XY plane, I'll set z equal to 0. So that's what I'll do first. So I'm going to figure out where they intersect in the XY plane. Now this won't be the equation of the line, but it'll be getting me closer. So I have found a point on that line where they intersect. Here's one point. Next, what I've got to do is I have to find a vector that's going to be parallel to this line I'm looking for. I know a point, and now I need to find a vector that's going to be parallel to that. Now, I know that this line lies in both Q and R because it's their intersection line. This means that this line L is going to be orthogonal to both the normal vector of Q and the normal vector of R, because they're both lying in the plane. This means I'm going to do the cross product of these two normal vectors, and I'm going to get a vector that's parallel to L, and once I get that, I'm almost there. Now this line that I'm looking for, this line L, we know that this line is parallel to this guy. Alright? He's lying in this same direction as this vector, and he passes through this point. So he's going to pass through this point here, and he's going to be in the same direction as this vector. So what I'm going to do is go back from section 12.5 and write this in terms of parameters. And here you have it. This is our line. So my x is the 3 minus 3t, the y is the 1 plus 3t, and the z component is this minus 3t. And this would be the equation of the line that is the intersection of the. We're going to define cylinder to be something other than what we're used to. Cylinder in this case is the surface of all of the lines that go through this curve C. Now curve C is the red line, and all of those lines that go through C, and they're all parallel and passing through C, are going to make up this surface, and we're going to call that our cylinder. We're going to also define trace. Trace is the set of x and y points. We're looking at an xy trace here. If I were to look at the xz trace, it would be this set of points that goes from this side to this side. It goes up. The yz trace would go in this direction here. Alright, we're supposed to draw some of these cylinders, so I'll go through the steps drawing this. I see that there's really no z component here. I would like to get it in, it's an ellipse, so I want to get it in that general form and divide everything through by 16, so I'll get x squared over 4 squared plus y squared over 2 squared, and then a 1, and this allows me to see my ellipse that I have. Now we're going to go over to the book's graphics because this will help us to see how to draw this. Alright, first up I have an ellipse along the x. I go along the x4 and -4. Along the y I'm going 2 and -2 as per my equation. Then what you're supposed to do is just draw it along the axes first, an easy place to draw it, and then you're going to draw it because this one happens to be centered there. If it weren't, it wouldn't be quite as easy to draw, but we just shift it. Now I'm going to draw a second one slightly above, and then I'm going to start drawing lines through that, and then we draw a few more ellipses above and below, and here is our solid. Much better than I would have drawn, and there we are. For our B question, it was x minus sine z. It has no y component. It's just drawn as it would be just along the axis, just to draw a nice easy one. Then they want you to draw a few more. Then you're going to draw the parallel lines through those, and a few lighter ones along the edges for your curve C, and then you can shade it in, of course, and yours will look just like this, I'm sure, just as mine would have too. Next are some general guidelines when drawing quadratic surfaces. So we're going to watch as they animate our quadratic surfaces that they're going to draw for us, and these are the steps that they're going to go through. We're going to recognize it first as a quadratic, and then we're going to find our intercepts, then our traces once again, and then draw our figure. In number 8, they want us to draw an ellipsoid with A being 3, B being 4, and C being 5. So on the x component, notice if I were to look at the xy trace, where the z is 0, it would be along this path here, and you just draw that largest ellipse for that. Then you'll look at the yz and you'll draw that, what the yz would be, the yz would be with the x being 0, so yep, there he is, he's got along this way, and then you would do the xz where the y is 0, and that would be along the x and z, and you will notice that the z varies between the 5 and -5, the y, the 4 and -4, and yes, we all drew that on our pieces of paper. In example 9, if we were to look at this one, note that my x is going to range between the 4 and the -4, and the y, the 2 and -2. It is an ellipse in that xy plane where the z is the part of the vertical component. Notice that the vertex of this is the point 0, 0, 0, and yeah, I'm sure that'll look great on your paper too. Just running through these quickly. Here's one where we have with the x and the y, the x varying with the 2 and -2 there at that very first one, that vertex there, it's that very first ellipse, and because of this z component it is going outward and up. Just more surfaces that we're drawing. This is an elliptic cone, another hyperboloid. Lastly, we have generalizations, and this to me is the most important part of all. You already are going to know what it looks like if you can put them in these forms. You'll be finding your A, B, and your C on each of these. So to me, this is the most important little summary that you've got here for chapter 13. And that's it. Have a great day.